We're going to round out this week with the beginning of the last chapter that we're going to study in this class, which is Chapter 8, which is on relations. So we're going to start with Section 8.1, which is about relations on sets. So in Chapter 7, we focused on functions which were a special type of relation. The relations that are not functions may actually allow for an input x to have more than one output, or it may not have an output at all. So if you remember, we actually defined what a relation was back in section 7.1. We said a relation R from A to B is a subset of A times B, the Cartesian product. Given an ordered pair xy and A times B, x is related to y by R if and only if the ordered pair xy is in the relation R. The set A is called the domain of R, and the set B is called the codomain of R. So we already know what domain and codomain are, but let's add some notation. We didn't have notation for relation in the last time we talked about what it was. I just introduced the idea of what a relation was. So the notation for a relation R may be written symbolically as follows. If we write x, r, y, that means that the pair xy, the ordered pair xy, is in the relation R. It means that x is related to y by R. Right? X is related to y by R, is what we would say. The notation x, then r with a slash through it, then y, means that x is not related to y by R, meaning x, r with a slash, y, means that the ordered pair xy is not in R. So let's look at an example. If we define a relation L, so I'm not calling it R this time, I'm calling it L. If we define a relation L, and it is from real numbers to real numbers, and we define it as follows. For all real numbers x and y, x is related to y by L if and only if x is less than y. Then I want to know, is 1 L 1? Well, if we look at our definition, 1 L1 would mean, is x less than y? Is 1 less than 1? The answer is no, it's equal. And I didn't give less than or equal as the relation, I just said x is less than y. So in this case, we would say no, 1 is not less than 1. So now, is 1 L5? Is 1 related to 5 by L? Well, if we look, 1 to be related by L has to be less than 5. Is 1 less than 5? Yes, 1 is less than 5. How about, is 27 related to 21 by L? Well, is 27 less than 21? The answer is no. 27 is not less than 21. However, is negative 27 less than negative 21? If you have a hard time picturing this one, you can throw it on a quick number line. If you've got 0 here, -1, -2, all the way down, right? Here's down to -21, and we would have to keep going, right, to get to -27. So in fact, yes, -27 is less than -21. So we would say yes. -27 is less than -21. One last example on this problem is -7 related to 2 by L. That is to say, is -7 less than 2? And the answer is yes, -7 is less than 2. Let's look at a slightly different example. For example, 8.1.2, I define the relation D from integers to integers as follows. For every ordered pair mn that is in z by z, integer by integer, Cartesian product, m is related to n by d, right? M is related to n by d if and only if 2 divides the quantity m minus n. So the question is 4 related to 0 by d? To figure this out, we need to identify m and n. So here, m equals 4, n equals 0. That means m minus n equals 4 minus 0, which is 4. Does 2 divide 4? Right? That's our next question. Does 2 divide 4? And the question, or the answer is yes, right? 2 times 2 equals 4, so yes. So that means 4 is related to 0 by d. Let's see if the same thing holds up for 2 and 6. Is 2 related to 6 by d? Well, m equals 2, n equals 6, so m minus n would be 2 minus 6, which is negative 4. Does 2 divide negative 4? I hope you said yes, because we could say 2 times negative 2 would give us negative 4. So yes. What about 3 and negative 3? At first glance, you might think that 3 is not related to negative 3 by d, because they're both odd. And that might make it a little more difficult to get an even number. But something interesting happens when we plug them in. So we know m is equal to 3, n is now equal to negative 3, and m minus n then is 3 minus negative 3, which ends up being 3 plus 3, which is 6. The sum of two odd integers is even. So we end up asking, does 2 divide 6? And of course, 2 divides 6 because that's 2 times 3. So, yes. But of course, I'm going to try, I have to give you one that doesn't work. I have to try to give you one that we can't divide by 2. So let's try part D. Is 5 related to 2 by d? Well, m is 5, n is 2, which means m minus n is equal to 5 minus 2, which is 3. Does 2 divide 3? Well, no, because that's 2 times 1 plus 1. So, no, it doesn't. So in that case, we would say 5 is not related to 2 by d. So let's try listing 5 integers that are related to d by 1, or related by d to 1. So we're looking at all of these kind. All of these numbers where if I take one away, it's going to be divisible by 2. Think about this in another way. Being able to be divided by 2 means that we have what kind of a number? Odd or even? I hope you said even. Because if we can take 1 away from a number and make it even, then our relation will hold. So the best way to get an even number by subtracting 1 is to subtract it from an odd number. It won't work if you use another even, because 2 minus 1 is 1. 1 is not divisible by 2, or 2 doesn't divide 1. So let's try, I don't know. Let's see, we've done 5 and 2. Let's see here, what if we did 5 and 1? So if we did that, we would get 5 minus 1, which is 4, and 2 times 2 equals 4. So 2 divides 4, so that works. If we did -3, then we would have -3 minus 1 is -4. That would get us 2 times -2, which is -4. So therefore 2 divides -4. So that works. Let's see here. What if we did 1? Let's see what happens with 1. That's an odd number. 1 minus 1 equals 0. Can 2 divide 0? Why not? 0 divided by any number is just 0. So we can say 2 times 0 equals 0, which means 2 divides 0, so we're good. Let's see here, what else could we use? Let's do, what about 11? Well, we get 11 minus 1, which would give us 10, and 2 times 5 equals 10, which means that 2 divides 10, so that works. And if we did negative, let's do -13. -13 minus 1 gives us -14. Well, that would be 2 times -7 to get -14. So 2 divides -14. So that's also a yes. So the last question on this page asks us to prove that if Q is any odd integer, then Q is related to 1 by D. Well, we kind of came up with that rule just now when we were trying to figure out some numbers that would work. So this proof should hopefully be pretty straightforward. So let's see what we can do with it. So our statement here, right, our statement would be for all Q, and now remember these numbers were all limited to integers, so we would have to also limit Q to an integer. So for all Q in Z, if Q is odd, then Q is related to 1 by D. That's what we're trying to prove. So our proof here says, well, let's start with supposing P of X is true, right? Suppose Q is an odd integer. From there, we would say, by the definition of odd, by the definition of an odd integer, or by the definition of odd, we know then that Q equals 2k plus 1 for some integer k, right? Then we can also say by the definition of our relation D, if Q is related to 1 by D, so QD1 is true if and only if, oops, made my F a little funny, if and only if 2 divides Q minus 1. Right? That comes straight from the definition of our relation D here. We said MDN if and only if 2 divides M minus N. M is related to N by D if and only if 2 divides M minus N. Here, our M is Q, our N is 1. So Q is related to 1 by D if and only if 2 divides Q minus 1. So we plugged it into the definition up here at the top of this page. This definition here, where M is Q and N is 1. Q and 1. My screen's a little too small for me to show the whole thing and for you to still be able to read it. Sorry. It's a little easier when we do it together on Zoom. So now we know by the definition of D, Q is related to 1 by D if and only if 2 divides Q minus 1. So by substitution, we can say, I know that Q is 2K plus 1. So I can say then that Q minus 1 equals 2K plus 1 minus 1. Or 2K plus 1 minus 1, which is 2K for some integer K. So we can say then, by the definition of divisibility, since Q is an integer, since K is an integer, 2 divides 2K. So we can say then, by plugging back in, we know that 2K is Q minus 1. So it follows that 2 divides Q minus 1 by substitution, if you want to plug it back in. So therefore, by the definition of D, Q is related to 1 by D. And that's how we write a proof for a relation. We need to discuss the inverse of a relation. So just as functions had inverses, relations also have inverses. If we have a relation R that is a relation from A to B, then the relation R inverse from B to A can be defined by interchanging the elements of all the ordered pairs of relation R. What that means symbolically is that for all elements X in set A and all elements Y in set B, the ordered pair YX is in the inverse relation if and only if the ordered pair XY is in the relation. So let's look at an example of this. I think these are even more straightforward than inverse functions. So we have set A. A is the set of values 2, 3, and 4, set of elements 2, 3, and 4. B is the set of elements 2, 6, and 8. And R is the relation that is the divides relation from A to B. Defined as, I'll give it to you, for every ordered pair XY in the Cartesian product AB, A times B, and this is where we need to see, this is our relation, X is related to Y by R if and only if X divides Y. So X is related to Y by R if and only if X divides Y. So let's think this through. Which ordered pairs would be in R and which ordered pairs would be in R inverse? And then we're going to draw some arrow diagrams for both. So let's think about R. R would be the set of ordered pairs such that the element in X can divide the element in Y. So if we start with element 2, 2 can divide 2, 2 can divide 6, and 2 can divide 8. So let's start with just those 3 sets of ordered pairs XY that are in R. So we had 2, 2, 2, 6, and 2, 8. The 2 is from set A. The other 2, 6, and 8 are all elements in set B. Let's see if we have any other sets of elements, any other ordered pairs here that would satisfy our relation. So if we already looked at all the 2's, let's look at 3. 3 does not divide 2 evenly, but 3 does divide 6 evenly. 3 does not divide 8. But we now know we can add 3, 6. So now let's move on to 4. 4 does not divide 2 evenly. Remember, that would be 1/2. That's not the definition of divides. 4 does not divide 6, it has a remainder, and 4 does divide 8. So we can add 4, 8 as an ordered pair to our relation. Here's the fun part about our inverse. If you read strictly by this definition, it says for all x in set A and all y in set B, the ordered pairs y comma x are in the inverse relation if and only if the ordered pairs x, y are in the relation. Or if we read it backwards, x, y are ordered pairs in the relation, like we have here, if and only if then, well, we also have yx is in the inverse relation. So we can use this definition to help us state the ordered pairs in the inverse relation. All we're going to do is switch around the x and y values in every ordered pair that fits our relation. Every ordered pair that's in R, we will switch their order and they will be in R inverse. So the first one is still 2, 2. When you switch the x and the y, they're both 2. The second ordered pair becomes 6, 2. The third one becomes 8, 2. Fourth one is 6, 3. And the fifth one is 8, 4. There's no inverse relation itself that we're going to define here that they need to satisfy. They are simply in the inverse relation because they are in the relation. That is the definition. These ordered pairs are in the relation, so if you switch them around, switch the x and the y, those same ordered pairs are in the inverse. So what do these look like as arrow diagrams? Let's scoot it up just a little and let's look at our arrow diagrams. Let's start with R. Here's our A. Here's B. We know in A we have 2, 3, and 4. And in B we have 2, 6, and 8. Let's show their relation with a red arrow for R. So we know 2 goes to 2, 2 goes to 6, and 2 also maps to 8. We know that 3 is related to 6. We know 4 is related to 8. So they look pretty different than the functions we were looking at, the one-to-one and onto. But that's okay. Remember, functions are just a special type of relation. Let's look at an arrow diagram from A. Ooh, that was not good. None of these are really that good. I'm not a great artist. From A to B, let's look at our inverse relation, which would really go from not A to B, but goes from B to A. A still has 2, 3, and 4 in it, and B still has 2, 6, and 8. And we'll notice that 2 goes back to 2. Oops, I forgot to change colors. Here, let's see if it'll show up. Let's try yellow. So 2 goes back to 2. 6 goes back to 2. 8 goes back to 2. 6 goes back to 3. And 8 goes back to 4. It looks like the same arrow diagram with the arrows going in the opposite direction, because that's exactly what it is. The last topic we're going to cover in section 8.1 is on directed graphs of relations. So for the remainder of the material in this chapter that we're going to cover in 8.2 and 8.3, we're going to be discussing important properties of relations that are defined from a set to itself. So that is called a relation on a set. So a relation on a set A is a relation from A to A. When the relation R is defined on a set, the arrow diagram of the relation can be modified so that it becomes a directed graph. Instead of representing A as two separate sets of points, we're going to represent A only one time, and we're going to draw an arrow from each point of A to each related point. So every set of related elements in A is going to have an arrow. For all points x and y in A, there is an arrow from x to y if and only if x is related to y by r, which means, again, if and only if, the ordered pair xy is in the relation R. If there is a point that is related to itself, a loop is drawn from that point back to itself. So let's look at a pretty basic example of what this would look like. So we have a relation R on set A. Set A is the set of elements 0, 1, 2, and 3. We are defining R, a relation, as the set of ordered pairs 0, 0, 1, 2, 2, 2, 3, 1, 3, 2, and 3, 3. And we want to draw a directed graph of R. So what we're going to do is we're going to represent each element in A, 0, 1, 2, and 3. And we know that they are related in the manner that they're given in R. So R is a set of all the ordered pairs that are related. So the first ordered pair is 0, 0. That means 0 is related to itself. From there, we see that 1 is related to 2. 2 is related to itself. 3 is related to 1. 3 is related to 2. And 3 is related to itself. So that is our directed graph. That's all we have to do. But of course, there's always a more complicated version. What would this class be without its more complicated versions of everything? It would be boring, right? So let's look at another example of a directed graph. This time, R is given as a relationship and not as a set of ordered pairs. We're going to have to find those sets of ordered pairs. So for this one, we have a set A that is given as elements 3, 4, 5, 6, 7, and 8. And our relation R on A is defined as follows. For every x and y in A, x is related to y by R if and only if 2 divides the difference of x and y. So we want to draw our directed graph. There are lots of ways we can do this. One is to find all of the sets of values, all of those ordered pairs that are in R first, or you can do them as you go along. So I'm going to start with at least drawing. Here, let's draw out, let's see, we have 3, 4, 5, 6, 7, and 8. So these are all of the elements that are in A. Let's see what pairs end up being in R. Let's start with exploring this concept of a number being related back to itself. So if 3 is related to 3 by R, that would mean that 2 would be able to divide 3 minus 3, which would be 2 divide 0. And that works. So we can draw a loop around 3. In the same way, this is going to work for 4. It's going to work for 5, 6, 7, and 8, because the difference of a number in itself is always 0. 4 minus 4 is 0, 5 minus 5 is 0, 6 minus 6 is 0, 7 minus 7 is 0, and 8 minus 8 is 0. And all of them are a multiple of 2. So this will work. So 4, 5, 6, 7, and 8 work this way as well. Now comes the fun part. If you'll remember back to an earlier example, we actually did m minus n being divisible by 2. And we said when they had the same parity, their difference was even. So the same thing ends up holding here, right? If I did, if I wanted to find out if 3 was related to 4, let's try 5, 6, 7, and 8. Let's just do this with 3. Well, then we would know for each one, if that's the case, by the definition of our relation, then for all of these, 2 should divide our difference of 3 minus 4, 3 minus 5, 3 minus 6, 3 minus 7, 3 minus 8. And what that means for each one is, let's see, this would be 2 dividing, let's see, 3 minus 5 is negative 2. So that works. 3 minus 6 is negative 3. Not going to work. It's not a multiple of 2. 3 minus 7 is negative 4. That would work. And 3 minus 8 is negative 5. Not a multiple of 2. So if you'll notice, 3 is related to 5 by r, and 3 is related to 7 by r. So let's add those arrows. 3 to 5, 3 to 7. Here's the really cool thing, is that this relation actually works the same way in the opposite direction. If we did 5 to 3 and 7 to 3, we would find that they also work. Does 2 divide 5 minus 3? Well, absolutely, because that's 2. Does 2 divide 7 minus 3? Again, absolutely, because that is 4, which is a multiple of 2. So we can actually add an arrow back from 5 to 3 and from 7 to 3. What we end up finding out then is that in the same manner, 5 and 7 also work because their difference, no matter which way you go, is also 2. 7 minus 5 is 2, and 5 minus 7 is negative 2. So we can start to see maybe a pattern here, right? So 5 to 7 and 7 to 5 also work. So we'll write those down. Let's see here, 5 minus 7 gives us a negative 2, which is divisible by 2, and 7 minus 5 is just 2, which is a multiple of 2. So what ends up happening is the same, we find the same patterns hold true for sets of even numbers, or not sets, but for ordered pairs of evens. So they're not sets of evens. We'll say the same patterns hold true for pairings, there we go, pairings of even integers. So what ends up happening then is if we add those in, 8 minus 4 is 4, which is a multiple of 2. 4 minus 8, negative 4, a multiple of 2. 8 minus 6, 2, definitely multiple of 2. 6 minus 8, negative 2, multiple of 2. 6 minus 4, 2, it's a multiple of 2. 4 minus 6 is negative 2, which is also a multiple of 2. So while this one ends up looking more complicated and we had to use a defined relation to draw our directed graph, as long as you take the time to really understand what the relation means, Directed graphs can give you a whole lot of information about your relation in a very, very quick manner just by looking at them. Make sure you take some time to look through and try a few of the problems that are listed at the end of this section that are in your textbook.